Module 3 continued, Stoichiometry of Formulas and Equations, Section 3.3, Writing and Balancing Chemical Equations. Now that we know how to name compounds, know how to write chemical formulas, and know how to convert between grams and moles, we can now introduce you to how to write and balance chemical equations. The mole plays a very important role in clarifying the amounts of substance that take part in a chemical reaction. For example, let's look at what happens when hydrogen gas and fluorine gas react to form hydrogen fluoride gas. If we just look at this reaction on a mass scale, we would see when 1 mole of hydrogen gas, molar mass equal to 2.016 AMU, reacts with 1 mole of fluorine gas, 38.00 AMU, we would produce 2 moles of hydrogen fluoride gas, 40.02 AMU. The only real information this provides us is that mass was conserved during the course of this reaction. Now let's look at the same reaction on a molar scale. The balanced chemical equation tells us for every 1 mole of hydrogen gas we have, we need 1 mole of fluorine gas, and this will produce 2 moles of hydrogen fluoride gas. This slide shows us what is going on during this reaction on both a macroscopic and molecular levels. Take a look at the reaction that has taken place on this slide. Here, magnesium metal is reacting with oxygen gas to produce a new compound called magnesium oxide. We are able to see 3 different views of this reaction: a macroscopic view, an atomic scale view, and finally a view with chemical formulas in the balanced chemical equation. A chemical equation is a statement that uses chemical formulas to express the identities and quantities of the substances involved in a chemical or physical change. The left side of this equation shows the amounts of each substance before the change, and these are called reactants. The right side of the equation shows the amount present after the change, and this is called the products. A reaction arrow separates the reactants from products. All chemical equations must be balanced. A balanced chemical equation will contain the same number of each type of atoms on both sides of the equation. A chemical reaction that is balanced will ensure that the laws of mass of conservation and atomic theory are being followed. During a chemical process, atoms cannot be created, changed, or destroyed. They can only rearrange into different compounds. When balancing chemical equations, you can never change the subscripts of a chemical formula. Remember, a formula represents a fixed ratio of the elements in a compound, so a different ratio represents a different compound. Bottom line is this: if you change the subscripts, you change the identity of the compound. Let's use the chemical change that takes place in an old-fashioned photographic flashbulb. How many of you have ever used a camera that contains a flash bulb? Probably not too many, with the invention of the digital camera and the cameras that are on our smartphones. When the flash bulb flashes, magnesium wire reacts with oxygen gas to produce powdery magnesium oxide. Right now, all we have done was to make a chemical statement of what happens when a flash bulb flashes. In order to convert this chemical statement to a chemical equation, we need to follow some basic steps. Here are the steps to follow when balancing a chemical equation. These steps provide you with a logical way to balance chemical equations rather than to leave it up to trial and error, although sometimes trial and error may have to be used as well. We will go over each step briefly and then use these steps to write a balanced chemical equation that explains what happens when the flashbulb flashed. The first step is to translate the chemical statement into a chemical equation using chemical formulas to show the reactants and products. Step 2 involves balancing the atoms on both sides of the reaction arrow. Remember, a balanced chemical equation will contain the same number of and the same types of atoms on both sides of the equation. We balance atoms by placing a number in front of the chemical formula. This number is called a coefficient, or more specifically, a stoichiometric coefficient. You can only balance atoms by changing the coefficients. You can never balance atoms by changing the subscripts of the chemical formula. When balancing atoms, always start with the most complex substance, which is the one that contains the largest number of atoms or different types of atoms. Leave the least complex substances such as oxygen gas and water till the very end. The third step involves adjusting the coefficients. Coefficients in a balanced chemical equation should always be the smallest whole number coefficient. The fourth step is to check your work to make sure that both sides of the equation contain the same number and the same types of atoms. The last step is to specify the states of matter of each substance in the balanced chemical equation. If the substance is a solid, use a lowercase s in parentheses. If the substance is a liquid, use a lowercase l in parentheses. If the substance is a gas, use a lowercase g in parentheses. And finally, if the substance is dissolved in water, use a lowercase aq in parentheses, which indicates it is an aqueous solution. Now let's put these steps to work by writing and balancing the chemical change that takes place when the flashbulb flashed. Let's refresh our memory as to what our chemical statement told us about this reaction. Magnesium wire reacts with oxygen gas to produce a powdery magnesium oxide. The first step is to translate the chemical statement into a chemical equation with the reactants on the left-hand side of the equation and the products on the right-hand side of the equation, both sides separated by a reaction arrow. Remember that the reactants represent the substance before the chemical change and the products represent the substance after the chemical change. In our example, both magnesium wire and oxygen gas are reactants, and powdery magnesium oxide is the product. The atomic symbol for magnesium is Mg, and the molecular formula for oxygen is O2. Remember that oxygen gas is a diatomic molecule. We need to remember how to write and balance ionic compounds that we learned about in Chapter 2. The charge on magnesium ion is +2 and the charge on the oxide ion is -2. Therefore, the chemical formula for magnesium oxide is MgO. Step 2 is the balancing of the atoms. We also want to start with the most complex substance, which is magnesium oxide, which is on the product side. Magnesium oxide contains one magnesium atom and one oxygen atom, so we put a 1 in front of magnesium oxide. In order to balance the magnesium on the reactant side of the equation, we need to put a 1 in front of it as well. Now that we have one oxygen atom on the product side and two oxygen atoms on the reactant side, so to balance the oxygen atoms, let's put a 1/2 in front of O2. Okay, we're starting to look like we have a chemical equation. Step 3 is where we adjust the coefficients. We want all the coefficients to be the smallest whole number coefficients possible. 1/2 of an O2 molecule cannot exist, so we need to multiply the entire equation by 2. When we do this, we get 2 moles of magnesium plus 1 mole of O2 produces 2 moles of magnesium oxide. We can omit the 1 in front of O2 as it is implied to be there. Step 4 is checking to see that both sides of the equation contain the same number and types of atoms. Notice on the reactant side we have 2 magnesium atoms and 2 oxygen atoms, and on the product side we have 2 magnesium atoms and 2 oxygen atoms. Therefore, our equation is balanced. All we have to do in step 5 is to specify the states of matter. Just by our limited chemistry knowledge, we know the states of matter for more compounds than we think. We know water is a liquid, oxygen, nitrogen are gases, and all metals are solids except for mercury, which is a liquid. Most of the time, the state of matter will be given to you in the chemical statement, which is true for our statement, which stated we have magnesium wire, which is a solid, oxygen gas, enough said, and powdery magnesium oxide, which implies our product is also a solid. Put in the states of matter and we are done balancing this equation. So now let's work through a sample problem. In this sample problem, we are asked to come up with a balanced chemical equation for the following chemical statement. Octane, which has the chemical formula C8H18, one of the components of gasoline, is mixed with oxygen from the air and burns to form carbon dioxide and water. Step 1 is to translate the chemical statement into a chemical equation with the line in front of all the reactants and products where the coefficients will eventually go. So our chemical statement and our chemical equation can be seen here. Step 2 is to balance the atoms, so let's start with carbon. This is a combustion reaction, so all of the carbon and octane will end up in carbon dioxide. Notice there are 8 carbon atoms on the reactant side, so we need 8 carbons on the product side, so put an 8 in front of carbon dioxide. The hydrogen atoms in octane will end up in water. There are 18 hydrogen atoms on the reactant side of the equation and only 2 hydrogen atoms on the product side. In order to balance the hydrogen atoms, we need to put a 9 in front of the water. The only thing left to balance is the oxygen. There are 16 plus 9, or 25 oxygen atoms on the product side of the equation and only 2 oxygen atoms on the reactant side of the equation. In order to balance oxygen, we need to place the coefficient of 25 halves in front of oxygen gas. Step 3 is adjusting the coefficients. We cannot have a fraction of an atom or molecule in a balanced chemical equation. Therefore, we need to multiply the entire equation by some whole number integer so that we get rid of the fraction in front of oxygen gas. So now multiply the entire equation by 2 to get 2C8H18 plus 25O2 will produce 16CO2 plus 18H2O. Step 4 is to check to see that we have the same number and types of atoms on both sides of the equation. Both sides of the equation contain 16 carbon atoms, 36 hydrogen atoms, and 50 oxygen atoms, so the equation is balanced. In the last step, we need to specify the states of matter. Octane is a liquid, and the rest of the compounds are gases. Now work through the follow-up problem before moving on to the next slide. A great way to focus on the rearrangement of atoms from reactants to products is by visualizing an equation as a molecular scene. Here is a representation of the combustion of octane we just balanced. Now let's work through a sample problem to do the reverse. Derive a balanced chemical equation from a molecular scene. The molecular scene in this problem depicts an important reaction in nitrogen chemistry. The blue spheres represent nitrogen and the red spheres represent oxygen. We need to write a balanced chemical equation for this reaction. So what is our plan to solve this problem? To write a balanced chemical equation, we first have to determine the formulas of the molecules and obtain a coefficient by counting the number of each molecule. Then we rearrange this information in the correct equation format using the smallest whole number coefficient and including the states of matter. Try writing the balanced chemical equation for this molecular scene before moving on to the next slide where you can check your work. So how did you do? Did you come up with the correct balance equation? If yes, great job. If no, can you see why you did not come up with the correct reaction? If you are still unsure why your reaction is not correct, please send me an email and I will try to help you.